did with one of my PhD students who's now graduated. His name is Akhtar Hussain. He's from Bangladesh. And Aladdin Buin, he was also my ex-PhD student. So now he is in New York, and he has a startup company to build a lot of the software that we worked on. Okay, so I'll give you, this is the outline of my talk, basically motivation and the fundus photography and OCT imaging, just in case people don't know what these are, and then a little bit of anatomy of retinal, retina and choroid. And this is, of course, his thesis aims and challenges that we looked at, and the methods we have solved and conclusions. Okay, so just to give the motivation, the life expectancy is going up, as you all know. Even in developing countries, people are living much longer because of improvement in sanitation and improvement in antibiotics. So this is really making people live longer. But it is also causing lots of problems from a health point of view. One of the real difficulties people have is related to loss of sight. For example, one of the things called age-related macular degeneration, AMD, nearly about 35% of the adults above 80 years will suffer from age-related macular degeneration. Basically, what it means is the retina basically is getting damaged. The other serious problem that we face is diabetic situation. That diabetes is quite prevalent, especially in developed countries, and also in developing countries. Diabetes is on a huge rise. Type 1 is very rare, but type 2 is very, very common. Nearly 80% of all patients who have had diabetes over 20 years are going to have severe eye problems. Glaucoma is another one. It is generally due to pressure in the eye that causes nearly 9 to 12% of cases of blindness. The size of population with these eye diseases is increasing enormously. For example, in the last 10 years, the number of people suffering either from AMD or diabetic retinopathy is already gone by 1.5 times. So this is over 10 years, and these numbers will keep increasing. So let's say this is a normal vision from a person point of view, but if they have diabetic retinopathy, what it means is part of this retina is basically damaged. You can see this part of the eye is gone. Wherever this black spot's there, basically the retina is damaged in those places. Whereas glaucoma, basically what happens is the peripheral vision goes away. The central vision is reasonably intact, but the peripheral will go away. Age-related macular degeneration, the central vision goes away, peripheral vision might be lucky to stay around. So the question is that we needed to make sure that these three cases are controlled in a reasonable way by doing early detection. As you probably know, once retina is damaged, there is almost no chance to reverse it unless breakthroughs happen through some kind of stem cell therapy, which might happen. Early detection is very important because many of these eye diseases, you can take appropriate intervention to slow down these the progression of this, or in some cases you can actually stop it. But of course, you can never reinstate the vision. Anything is lost is lost. So therefore, it's if to do large-scale things, you really need some computerized methods. That's the only way you can do that. More than 1 billion people need to be, regularly. Once every 6 months, around that kind of period, you have to do the eye testing. We need automated tools for doing that. But the nicest thing is these are very non-intervention methods. That means there are no medical procedures except very passive, like a photograph, taking a photograph. And of course, if we have these methods, if we can scale it, improve quality of life by preventing blindness or slowing down the progression of blindness. Of course, it also helps large-scale analysis of image analysis you can do, because manually doing this is just impossible, as I'll show you how tedious these things are. So basically, economics, if you can even improve sight by 4 or 5 years, that would be a huge saving for the society in terms of medical costs and also quality of life the individuals would have. Okay, so the first thing is fundus photography. It's basically taking the picture of your retina going through the pupil. I think in 1910, Goldstrand received Nobel Prize for being able to take the picture of the retina. As you can see in the retina, this is the healthy retina, and this is a person who had some eye diseases, and you can see it is not very clear images anymore. And I have an enlarged version here just to show you. This is called optic disc. This is where we don't have any vision at all. All the blood vessels and the optic nerve goes through this part of the area, and the optic nerve goes into the brain, and that's where we perceive vision. And this is your macula. This is where the best eyesight we have. So the number of if you use camera words like pixels, that you have highest several hundreds of millions of visual parts takes place here. And all this retina is actually is a peripheral vision, but this is where we see the most high precision of the sight takes place. And this is where the damage took place. As you can see, a kind of white kind of stuff it is. There's like some kind of calcification or some kind of death of a tissue, and this is what makes the vision completely black for those individuals wherever these things are happening. But the interesting thing is that even though the individual has such a severe damage, the human brain compensates quite a lot. People do not realize they have these diseases because they seem to manage very well, their day-to-day life. They can do certain things, they may not see it, but they just ignore it rather than seeing it as a problem. So this is the main issue, that why you need regular testing need to be done. So in 1991, Huang developed the optical coherence tomography. That's my main talk here. The reason is this is much better technology to understand what's happening in the human eye. So it's capable of going through the layers of retina. So for example, in this image, let's say this is the top surface of the retina you're seeing. Now what we want to go is we want to go inside the retina, and we want to see these layers. So this is a particular cross-sectional view of retina, and this is the macula. This is where we have the acute eyesight that is possible. And you can see there's lots of tissue layers within the system. For an ophthalmologist, they're really interested in these, how healthy these layers are, and they really need to know the boundary layers and how they are separated. In fact, you can measure various kind of biomarkers from these layers and then actually tell how healthy this individual is. And you can see in the disease case, this is not smooth anymore. And these are called Drusens. Basically, what happens in the retina gets shape changed. And in fact, even the focus of the human eye might change because the surface changed a lot. But then, of course, again, the brain slowly compensates these things, and people don't perceive that something has gone wrong for them. Okay, this is the healthy eye, and this is the other one. So what we really need to do is need to find how we can find these layers. Just to give you what OCT does is a light is transmitted. This is a low coherent light. That means you have many wavelengths, and then the light falls into the eye, and the reflected eye will have a different phase depending on the layer thicknesses, and that difference in the phase shift is what you can measure the layers. And of course, the intensities will vary, and that tells us the layer thicknesses, and these boundary layers are known as a result of that. As light penetrates, as you can see, the reflector light from the very deep layers to outside will be a lot less, and you see generally much less information we can gather by using this kind of technology. So this device right now is about, I think, around 15,000 to 50,000, depending on the quality of machines you have. But there's a lot of effort going on to make these devices around $5,000. If that's the case, even small villages can afford to buy these things. And because this is a non-intrusive mechanisms, people can actually take images of human eyes without having a huge skill basis. So it is quite practical. Whereas Fundus one, the one I told you, is in fact can be done using a smartphone. You can get probably around $3 or $4 lens units you can mount on your camera, and you can actually take a picture of the eye. So this is also quite a large interest to study from the Fundus images. So there are various kinds of models that are come into the system. For those who know MRI, you realize there's lots of techniques within MRI. And similarly here as well, you can do time domain model, or you can use the frequency domain. Each one has a different. Time domain is much more longer procedure because you have to adjust the lens continuously to track the signals, whereas the frequency domain is much quicker. You take one shot and very quickly the image can be captured. And there's a swept source, which is a combination of both the time domain as well as the spectral domain. The combination of that gives you much better imaging, but it's a slower process. So just to show you, this is the optic disc. When you look at the depth, you can see, it's quite a concave shape. And to track the layers along these boundaries are very, very, very difficult. For glaucoma, you really need to know the ratio between these red lines and the yellow lines and the other side as well. So this is basically tells us whether the person has glaucoma or not. So that means if this optic disc is very small, they're going to lose vision again. So these are very important biomarkers. So sometimes optic disc, optic cup is inside. The ratio between these two is an important biomarker for glaucoma. And these are the blood vessels. And a really interesting thing is that by looking at these blood vessels, you can tell whether someone is suffering from diabetes, and we can also tell whether they have, for example, whether they have hypertension. And looking at the quality of the rest of the retina, we can also tell, almost you can predict with a very high accuracy whether this individual will have heart attack or a stroke in the next 3 to 5 years with a very incredible reliability. And earlier, one of my PhD students did some work on seeing whether the correlation between the health of the retina and the person's MRI. So we looked at there's a high correlation between the some of the Drusen area, which I'll show you, versus scars in the brain. So in fact, you can tell by looking at the eye is whether the person should have an MRI. The question is, you can get MRI, but can we treat them is a different question. But at least you know that they are prone to either heart attack or a stroke. So lifestyles might be changed, or they might decide, okay, I'm not going to work on this Google project anymore and have a holiday. So if it's going to cause stress, it's not a bad option. Okay, so whereas the OCT image is much more detailed, as you can see, this only shows the surface of the retina, but here you can actually see the inner layers of the retina. So again, showing you this in an enlarged version, and it's the OCT image looks like. And then if you do the 3D modeling of this OCT, because you can get many cross-sectional views and you can stitch them together, and you can actually make a multi-layered like cake. You can see that. You can see it is a huge pit where the optic disc is basically, all the blood vessels and optic nerve go through that part of the space of the eye. And this is the macula. And you can see a little pit here. I don't know why biologically we have such a pit is unclear. The one possibility is that you increase the surface area in a small area so that you have many more sensors located in that space. That's the only explanation I have. But there may be other biological reasons why we have this kind of a pit in that space. Again, you can see 3D view. You can build these layers. So now I'm going to quickly introduce some of the layers. It is not important to understand this talk, but basically for an ophthalmologist, these are extremely important to understand various layers. The very first one is called internal limiting membrane. Basically, it separates, this is basically the surface of the retina. If you take a fundus camera, you basically see the top layer from a surface point of view. And then this is called choroid. The choroid is the one that supports the rest of the retina. Sometimes, when people get older, or they don't have to be very old, sometimes the retina can be detached. Detached means this part, the whole layer can come out, and it has to be put back within a short period. And sometimes what they do is they make the person, legs up in the air and they head down so that the gravity will help them to put the retina back again. And then sometimes they use laser beam to stitch it, to stick it to the surface again. And I have known people who had retinal detachment. It is not that uncommon. Choroid is the one that actually helps your blood circulation and various fluids to the eye, and also absorbs any excess light so that the retina is not damaged. I don't know whether you have read some history probably about Darwin. Darwin, of course, the first person who probably never believed the existence of God may be Darwin, but even he had doubts looking at the human eye, whether this could have ever evolved by evolutionary mechanism. It's so complicated organism. Would this be possible? But of course, we know this is possible because people have found some of the fish extremely deep oceans. There is no light, therefore the eye did not develop them. But apparently, when they were brought to the surface, the eye started developing in those fish as well. So you can see that this is an evolutionary mechanism. But the most important thing that I wanted to say is before we started this work, almost there's no existing automated tools that can actually separate all these 10 layers of retina. And we were the first ones to do this to best of our knowledge. So basically what we need to do is we need to find these boundaries and measure various kind of thicknesses, and therefore we can do that. So just to show you here, this is let's say, patient sitting in front of this OCT instrument. So basically you scan through this line, it's going inside the retina, and that's the image you build from that point. This point is same as that point, and this point is same as this point. And we're going inside the retina and we construct these things. And these are the various kind of layers. This is the choroid is that area, and scleria is that area. Okay, so the Bruce membrane is also a very important area, this yellow part area, and that also an important biomarker to recognize how healthy a person's eye is. So here is the fundus camera picture. A particular patch is taken, and if you see that through a line, and you can see there's a damage here, and you see a huge like a cyst form here. It is called microaneurysm. Microaneurysm means actually blood clot. A leaking of blood that took place here. And then here is the geographic atrophy. That means actually the degradation of tissue. And you can see this is how it looks like with OCT image. And these are the Drusens. These are basically some kind of white matter. So basically this whole layer gets bulged out wherever these white spots are there. And this is a cyst, a form of extra tissue formation that also pushes the contours of the retina. So why these are important is, like, for layer thickness, for example, change in thickness of the retina in its layers is a characteristics of many diseases such as glaucoma, age-related macular degeneration. For example, glaucoma patient has 20% less of retinal nerve fiber layer and thickness than normal patients. And inner retinal lesions, that is any scars or any damages, typically is related to diabetic problems. The Drusen is actually characteristic of, again, age-related macular degeneration. Cup disc ratio is basically glaucoma, as I said earlier. If the cup is very small, there's a good chance that they can actually lose sight. And in fact, you can tell almost very accurately in how many years they're going to lose eyesight. And one of the ways to, at least control that is to reduce the pressure in the eyeball. So to develop the SDD images, we basically need to find the boundaries of these retinal layers, and then we also need to find the choroid, and then need to recognize pathologies. And then we need to measure thicknesses of these retinal layers and cup disc ratio. All of these things, if you do that, we can do a phenomenal accuracy. You can do that. So you can see these are the boundary layers. And remember, this is how an ophthalmologist has to draw the lines and need to measure the thicknesses before they can quantify that. And if they have a Drusen, and you can see these layers gets really mixed up. And automated tools to do these things is a real challenge. And then you have these anatomical features that makes it even harder. So in these areas, to track the boundary layers is extremely difficult. So for example, if you have a Drusen or it's a kind of pathology, so pathology means basically a damaged tissue, damages. And again, this is the issue. And again, I said, this is the macula. Again, the shape is like a cup, and many layers becomes incredibly thin here, and tracking the layers is very difficult. This is normal macula, and then macula with the Drusen. So if a person has eye diseases, basically they have a lot of changes in the structures. And then macula with the Drusen, and also geographic atrophy, that is basically damaged tissue. So this is how the images generally will be taken. This is relatively less noise. This is enhanced the OCT image, and this is a noisy SD image. Because remember, this is a passive device, and the signals are extremely weak. And then you're trying to do. And you can also see some kind of shadows also happens. You can see that this is some kind of a obstructive tissue, and then the whole signal is blocked all the way, and you can see these things are happening. So that means if you're trying to track a boundary, then all of a sudden you have shadows coming, and then trying to fill those things will be very difficult. And then you will have variation of intensities, even though the tissue is very homogeneous, but because the light has to penetrate through, the refracted light will not be the same. It varies from point to point. And it's an enlarged version of shadow effect. As you can see, the boundary is very clear here, and then it becomes incredibly shadowed area. Again here, and the challenge 6 is that some of these areas, the limiting membrane is the thickness variations can vary quite a lot, and then tracking these lines will be, you can see extremely very thin layer. Then we needed to build 3D segmentation. So basically, what we do is we built 2D segmentation for each of these scans. We call them B scans, the ones I showed you, and then those layers can be stitched together to form a 3D representation. So typically, I'll show you B scan in a minute, and then we have to reduce the noise, apply some filters, And then first thing we need to do is we need to find the area of interest, region of interest. And this we do by approximately detecting 3 reference layers. And that gives us the guidance where to look for these boundaries. From that, we detect the inner limiting membrane and retinal neural layers, and then refine from that, and then we detect the boundaries. So first we do Wiener filter, anisotropic filter we apply so that the same image is much more smooth, and now we can track these boundaries a little bit more easily. So the way you can see is that, by the way, this is called the B-scan. This is called B-scan, and vertical line is called A-scan, a vertical line. So here, this is the vertical line that I was trying to show you. So basically what we do is we track the intensity from this point to this point. This is how the intensity varies. So these points are guidelines for us as an approximate positions of these layers. So we label these pixels, and that gives us the boundary lines. So basically we define how to locate those boundary lines. And this is the formula we use to detect along this line to mark those pixels. So first thing we do is once you get these approximate layers. So this is the first original image, and then we do the edge pixels. We do canny filter we run, and then this gives you basically the gradients. And then what we do is that from this, we want to select various kind of nodes. The nodes will be defined in the following way. That means some of these edges are positive gradient, some are negative gradient. So we construct a graph using these kind of, so basically what we have is, these are the some of the boundaries that we defined earlier. I told you approximate boundary layers, and that helps us to be interested in those edge pixels that we can use for constructing it. So the way we're going to do is that, let's say this is after canny, and this is our boundary. So this is our area of interest. So the next thing we need to do is we need to somehow stitch all these pixels so that we can form a boundary layer. So basically what we did is that all these edges are actually mapped into a graph. So we construct a graph such that we can define the distance between various pixels or the group of pixels by constructing some kind of edge weights we can give them. And then we basically find the shortest path. And the shortest path happens to be one of these boundary lines. So basically, these are the pixels enlarged here. You can see that all of these are adjacent pixels in a particular gradient. And then this is another one, and there's a gap here, and there's a group of pixels like this. And now the question is, we construct a fully connected graph, and then we provide some kind of edge weights between these kind of nodes. And the edge weights are based on, for example, how far away these are, how much elevation they have from the current position. One of the things we try to do is these boundaries, you don't want the boundary to go up. It tries to be horizontal as much as possible. So these are the kind of constraints you have to do that. And of these are actually learned from various manually graded images. So once you have that, this is what you have, and then you can see some breaks in it. Then basically we do standard interpolation to construct the whole graph. And this is how the final boundary is built. So here is the kind of enlarged image showing red color pixels, positive vertical gradient in these things, and the green colors are negative vertical. So basically you can track these things. So basically the same image shown here. For various layers, we basically repeatedly apply the same methods. So contiguously within 3 by 3 neighborhood, candidate pixels are grouped based on the number of pixels called pixel group, and the end pixels of each group are basically called nodes. So this is how this is a group of pixels. So that's the node 1, node 2 of those group pixels, and now we have to connect them. So the edge weight is defined by using these 3 parameters. Between 2 nodes A and B, the weight of the edge. So phi of AB represent the spatial distance if they're far away, and of course the edge weight is very high. And the second one is the psi of represent the slope between A and B. So for example, if the pixels are vertical, for example, you give the maximal weight, maximal weight. And then psi represents how well the pixel group contained within the boundary match. So these 3 parameters effectively defines the edge weight. And here, in the nodes on a shortest path boundary, basically we connect them in this example to show that 2 and 3 are closer. So therefore, we make that connection, and therefore all these pixels are basically ignored. So basically, we do the compute shortest path with that, and this is what we have managed to construct. So the data sets we use is again in this area. A lot of medical guys, they look at these images and they just do the diagnosis without really doing too much manually computing. They only do the manual gradation for publishing papers, but in the actual diagnostics, they just look at it. Okay, this is the problem, and this is how they do it. But for large-scale studies, you can't have ophthalmologists to visually inspect every image. So you need to do that. So we have 20 subjects with various stages of the eye diseases they had. We have 11 B scans. That means 220 B scans we had. There are 10 healthy subjects, 10 B scans per subject. There were 100 B scans we have. We have Centre for Eye Research in Australia. It's quite a large publicly funded eye research center. So they've given us some data sets, 15 subjects having varying stages of age-related macular degeneration. And we have 49 B scans for each subject. And each scan is of image size of these many pixels. Middle 5 B scans for each subject has been manually segmented. So this is the original image, and then somebody patiently sits together and then draws these boundary layers for various images. We haven't shown all the 10 layers, but here only some of them are shown. So there are various people have done that. A lot of attempts has been happening for the last 5 to 10 years in this area. And you can see this is the real manual segmentation, and you can see cannot detect the boundary properly. And you can see, this particular layer is completely misclassified by this method. Again, this is the CHU. This is one of the state-of-the-art method. This also failed badly because this is what it should be, but it was tracking along those lines. And DAFOR is another method. All of these methods are based on intensity-based algorithms with various kind of approaches they have done. Again, Drusen area, green boundary, was not tracking properly. For example, it should be on top of that, it was below the Drusen area. The Iowa method is, again, missed this particular layer, completely misrepresented. And this is Aurora method, again, similar problem. So whereas the shortest path method has done exceptionally well in all these areas. When the image is very clean, it's no problem. All the methods do pretty well. Only when there are diseases, that's exactly where you really want to do segmentation well. All those methods have failed, and this seems to track exceptionally well. So this is just a comparison. You can see that you basically this tells you with respect to the manual segmentation how much deviation these layers went through. This is effectively, at each pixel position, you have about 13 pixel positions drifted by these methods. Whereas our method, as you can see, it is in ballpark within 2 pixels on average, compared to these about 16, 7, and so on. So this paper appeared in last year, or debuted in 2016, RTP transactions. Similarly, choroid also, we could do that, so I don't want to go through that. This is much harder because of the intensities are much more difficult, so you really need a good intensity normalization. That's basically what we did and were able to do properly. So we did the 2D segmentation for this, and again, results were very, very accurate compared to some of the previous methods. So you can see the tracking has been very good, irrespective of some of the pathologies in the eye. So we were able to do 3D segmentation as well, based on the 2D segmentation. And then what we do is we take these layers and then do the correlation between layers and then basically map into 3D. So these are the 3D structures. The student was exceptional. The guy built the whole system, and the ophthalmologists were really impressed. And now they're actually using in their studies. It's all written in MATLAB, so very slow, but so we actually done the biomarkers. We got all the segmentation. We constructed various extractions we did using lots of images. And you can see once you do the 3D, the accuracy really improves much, much higher because we have more data points to correlate. And you can see this is less than 1 pixel width of errors that we could get. And also you can see the deviation is also very, very small. So we can basically do all the layers within the system. Okay, this is we were able to, this is the picture to show you all the 10 layers we were able to segment even in the presence of Drusen. Again, another example, we have cysts in this, and yet we were able to get all the layers. And again, a very large cyst happened. You can see the whole eye contour has changed because a lot of swelling in the tissue area, and still we were able to track all of them exceptionally well. So this is the overall performance. Okay, other thing we try to show is when you do the 3D, how many B scans you have to take. The more scans you take, of course, more accurate you do. And what we were able to show, even with 10 scans, you can get very useful analysis you can do. So this is a quite acceptable error as far as diagnostics concerned. And we can do optic disc as well using the same technique. And this is very important for glaucoma detection. And you can see that we can track these layers exceptionally well. And this is the top view of the retina, and we actually show you the optic disc cup. We can look at that. So this is actually Drusen. This is the damage of the eye that manually graded, and this is the automated. It doesn't match perfectly well, but from a diagnostics point of view, this is exceptionally, very, very accurate in terms of diagnosis purposes. Again, this is the original image, and then this is manually graded, and you can see that most of the major pathologies were detected by the system. So we have 45 cases. This is, I think, New York data, I think, from Srinivasan. 15 patients with diabetic macular edema. Edema means swelling. And then this is the age-related macular degeneration, and 15 control or normal people. And then second data set contains 72 cases, 15 people with diabetic macular edema, 28 AMD, and 28 normal, 29 normal. So we did the same thing, and we tried to do the classification. We basically get the volumes of lesions, and we get the Drusen, curviness, and then we also do the these OPL and ONL boundaries we extracted, and the thickness is computed from those boundaries. So, for example, this is a curviness 0. That means basically very smooth contours here, and the curviness gone up because you can see the Drusen, and it's even worse. The curviness is very high. So we also have another data set. This is the Duke one that I was talking, Srinivasan, the Center for Eye Research, and the New York. So basically we have 3. This is from Australia, this is from New York, and this is also from Duke University. So these are the data sets we have. And we basically done 15-fold cross-validation on these data sets. And the most important thing you can see is that diagnostics is phenomenally accurate. We can accuracy is nearly 97%, and you can see both sensitivity and specificity is very, very high. So from our point of view, it is completely doable to do fully automated accuracy for early diagnostics. Again, we tried various logistic regression support. Even naive-based does exceptionally well. Part of the reason is, people might be surprised why naive-based doing so well. The reason is these biomarkers are well studied by ophthalmologists. They are very good biomarkers. And once you extract them, any model would work exceptionally well. So this is not surprising that these methods work so well. But certainly what we found is random forest and then, or decision trees does exceptionally well. Even regression, decision-based regression also works exceptionally well for these things. We built a tool called OCT Inspector, basically, just to show you. It does lots of things. Also allows you manual correction, and then you can retrain the system whenever things are, or error, for example, an ophthalmologist can correct it, and then they can extract the things. They can do lots of visualization. So, for example, they can see, this is, for example, macula, and you can see various layers they can do. They can color them, and then they can see a particular layers they want to see. You can remove certain layers and actually see inside layers what's happening. And then they can see cross-sectional views, and they can measure, these optic disc ratios. All of these things they can measure very accurately. So basically, we showed that it is a, interesting algorithmic-wise we can do it. We haven't, from a machine learning point of view, the only thing we have done is we needed to estimate some coefficients, which we tried on some manually graded images were used to estimate these parameters. And there's so many parameters, the technique that we used is simple similarity annealing was able to find reasonable values, and they seem to be pretty robust, because when we change those values, plus or minus 10%, still the system performed exceptionally well. So that means the stability of these parameters are pretty good. Then, of course, we wanted to see whether, rather than going through all of this, can we do a shortcut using deep neural nets? You guys might know UNet is one of the very popular segmentation network. They're called UNet because the network looks like a U shape. It has a lot of various deep neural net structures in it, lots of convolution nets and so on. So basically, we used, contracting path and expansion path, upsampling 3x3 and skip connections, fully convolutions, dropouts applied for middle layers, 23 convolution layers in total. So what we did is we needed to do patch-wise to learn, and then and corresponding ground truth were fed to make this net to learn. Again, same data set used. Analysis Xavier uniform initializer. Patch size, patches we use is 480 by 48 height width. Patches of 32. Stochastic gradient method used. Loss function is categorical cross entropy. learning rate 0.01, epochs 150, and of course we use Google machine. We don't have any good computing in the department. So this is the configuration. It took about 20 hours to train the system. So this is the system. So this gives you probability map and the probability map for boundary IZ. So various layers we have shown. These the boundary map. They are, the whiter means higher probability. So this is the manual one. This is the graded one. You can see it's done up pretty good. But the important thing is we still need to apply our shortest path segmentation algorithm. UNet alone can't find your boundaries because it gives you the probability for each of these pixels, how likely it is to belong to a particular boundary cell. Then we apply exactly the same path segmentation algorithm we have used and done it pretty well. Again, I think the same map for another image. So here you can see with the Drusen, managed to track well. And again, you can see it done exceptionally well. This is with the macula. And again, this is very difficult area. And you can see still able to track them exceptionally well. And again, you can see very competitive with all these methods. This has just happened like a few days ago. We still need to look at these results a bit more carefully. This is done by a master's student part-time. So we have a master's coursework, but they do about, I think it's a 2-year program, constitutes 200 points. Out of those 200, 75 points is for research. So basically the student has done this work trying to build this. It's for a 75 points is quite a lot because they're not exposed as much to deep learning. So the person has to learn deep learning, need to learn, TensorFlow software, how to run it. Initially it was run on his Mac, sweating, with a few images, and results were horrible. And finally we convinced him, he begged somebody to provide computing facilities. Luckily he got access to the Google machine. I was quite impressed that he managed to get these results without doing too much work. But the important thing that he did in the last 15 days is basically applying the shortest path algorithm using these weight techniques that really help to reduce the error. So lots of papers. So basically, that's the end of the talk. If these slides are available. Okay, so I managed to finish in 50 minutes.
Which did better, your first method or the neural net?
First method is still very good, extremely fast, because we know the anatomy of the eye. And here the system has to learn somehow. But the interesting thing is, still is surprising that without too much manual tuning, we're able to get, within 10% of the results.
Is it possible the shortest path objective can be blended into the
learning? I'm not sure. Probably it can be, because I heard that some people were able to find shortest paths using deep neural nets. You heard about this? No, I heard that. I mean, in general, you can't, because on a particular image size, I think you can do, or less than certain image size, you can do it. But remember, this image is too big. You can't. I don't think we can make the system to learn the whole network. But certainly, there's a promising results.
Okay. Yeah, thanks. Thanks, speaker again.